Our next topic is electrolysis, and this is the next section in your chapter, electrolysis. We already discussed about conduction, so now we are moving to the electrolysis. First of all, let me define what is electrolysis. Electrolysis is nothing but it is the chemical decomposition of an electrolyte. Means we have an electrolyte, it undergoes a chemical decomposition. When it undergoes a chemical decomposition means by the passage of electricity through it. Okay, and moreover, the decomposed ions may attract towards the respective electrodes. The decomposed ions may attract towards the respective electrode, and this phenomenon which is said to be electrolysis. Okay, so what do you mean by electrolysis? It is a process of a conversion of or chemical decomposition of an electrolyte, and by the passage of electricity, and so that the ions formed are attracted towards the respective electrode. So, electrolysis is the process of chemical decomposition of an electrolyte. Process of chemical decomposition of an electrolyte by the passage of electricity. By the passage of electricity. Okay. Moreover, the formed ions attracted towards respective electrodes. They form some kind of ions, which are, we know the ions are cation and anion. We know, we are already familiar with that, and they are attracted towards the respective electrodes. And this process is known as electrolysis. Okay, electrolysis. Right. So it is a process of chemical decomposition of an electrolyte by the passage of electricity, so that the produced ions are attracted towards respective electrode. Listen here. Have an electrolyte AB. AB is my electrolyte. Okay. When electricity is passed, the AB is decomposed to two ions, that is A plus and B minus. And we know that A plus and B minus are the cations and anions, right? So what is A plus? It is cation. And what is A minus? It is anion. Ready? Fine. So the electrolyte is chemically decomposed into two when electricity is passed, and they form some kind of ions. For example, here is a cation, and which gain electron. Cation is a positive charged species. Okay. In order to deposit in a electrode, listen here. This is a main important point. Atom in zero state, if an element have two kind of states, that you know, I think. An element have two different type of states. That is, either it's zero state or it is in charged state. If an element is in zero state, then it is in electrode. It will be in electrode. Element, if an element is in a zero state, then that element should be in a electrode, because since it is an atomic form. Like if an element is in charged state means some kind of charge, maybe positive or negative, or in an anionic or cationic form, whatever it may be, then it won't be in a electrode. It should be in a electrolyte, or it should be in a solution. Okay, if an element is in a charged state, then it won't be in a electrode. It should be in a solution. Okay, it is in electrolytic solution, and this is a very important point. Okay, and one more point is the electrons are in electrode, not in solution. Always electrons are in electrode, not in solution. Keep it in mind. That is some kind of important points. So listen here. the forms A plus and B minus. Ready? Now, if the A plus, which is attracted towards a cation, which is attracted towards cathode, I think you're familiar with that. Okay. So here forms a cation, and the cation which is attracted towards, and they are attracted towards the respective electrode, means the cation should be attracted towards the cathode. Okay. How the cation absorb to the cathode? By a oxidation or a reduction? No doubt it is through a reduction, right? Because if A is in a cathode, then cathode is an electrode, right? Cathode is an electrode. So A plus means it is in solution, because ion is in solution. But if it is in electrode, then it should be in A0 or in a zero state, right? So how we can change a plus positive species to zero state? By gaining electron. That's why the process said to be reduction. So in cathode, it always reduction. Okay, and the reaction may be A plus plus 1 electron. It will be A0. This is a reaction. Okay, fine. What about the anion? Anion, which can attract towards what? Anode. Okay, whatever it may be, if an element goes to electrode, then it should be in a zero form. So in anode it will be in a B0 form. And now first of all it is in a B minus. Now it is in B0 form. Then what happens? The excess negative electron will be removed, or electron will be lost. The process oxidation. Okay, fine. So what happens to B? B minus simply lost one electron and it become B. B minus simply lost one electron and become B. This is a process. So this process is known as electrolysis. So electrolysis is a process of chemical decomposition of an electrolyte. It is a process of chemical decomposition of an electrolyte by the passage of electricity. And they may form some kind of ions, and they can attract towards the respective electrode through oxidation and reduction. So it is clear that here is an oxidation and reduction, right? Yes. And the redox reaction is here. For that redox reaction, first of all, you have to supply electricity, right? So here the energy change is electrical energy, which turns to a chemical reaction, which means electrical energy turns to chemical energy. So the energy changes electrical energy to chemical energy. Okay. So it is clear that here is a redox reaction. My question is whether the reaction is spontaneous or non-spontaneous. Whether the redox reaction is spontaneous or non-spontaneous. No doubt it is non-spontaneous, because what do you mean by spontaneous process and non-spontaneous process? A spontaneous process, a process which can occur without any driving force. Okay, but here for the reduction and oxidation, there is some kind of external driving force. That force is your electricity, right? Yeah. So no doubts, this is non-spontaneous redox reaction. So here a non-spontaneous redox reaction occur or takes place. Okay, and the cell in which electrolysis takes place is known as electrolytic cell. Okay, cell in which electrolysis called a electrolytic cell. Aspect of electrolysis and qualitative aspect of electrolysis. Ready? So let me define the quantitative aspect of electrolysis. Quantitative aspect of electrolysis, and it is based on Faraday's law. What it is? Faraday's laws. Okay. So the first section in your electrolysis, quantitative aspect of electrolysis. Okay, quantitative aspect of electrolysis. So something about the quantity, right? the first one or the main concepts are quantitative aspect of electrolysis, which consists of Faraday's laws. You know, Michael Faraday. So Faraday's laws. Ready? And let me start with the first one. First law. Faraday's first law. And Faraday's first law is that I think you are familiar with an electrolytic cell. Huh? Let me draw an electrolytic cell. This will be the electrolytic cell. In electrolytic cell, both anode and cathode are placed in a single container. In a single container. Ready? And this is your cathode or anode. This is your cathode or anode. Whatever it may be. Something which connected with the constant DC source, or the positive terminal of constant DC source, what we called as anode here. Okay. So the electrode which is connected to the positive terminal of the DC source, which is said to be this is a constant DC source, because this here we have to supply a constant DC current. Then only the reaction takes place. And only we know that it requires a current first, right? Electricity first. Then only the chemical decomposition takes place. So this is the source which is responsible for the supply of current. Okay. And the positive terminal of that DC source may be connected with an electrode, and that electrode we can set it as anode. And if the so automatically this will be the cathode, right? Yeah. Fine. And here we filled what? Here we filled what? Here we filled the electrolyte. Let the electrolyte is an AB. AB is an electrolyte. So it is clear that AB electrolyte should have what? That AB electrolyte may have electrolytes may have the ions A plus and B minus, and the A plus, which is cation, which on reduction to attracted, undergoes reduction to attract, or the cathode, and B minus is the electrode, which on oxidation to attract the anode. Ready? Fine. Okay. Fine. And this is a simple setup of your electrolytic cell. So what about the first law means? We know that by passing the electricity, passing the electricity through electrodes to electrolyte, passing current through electrode to electrolyte, the deposition may take place, right? Yeah. If A is deposited here, there will be an increment of mass on that electrode, right? If A is deposited on that particular electrode, there will be an increment of mass. If 100 molecules of A deposited means 100 A particles is coated on that electrode, which means the mass of that substance is increased, or some kind of mass is deposited there, right? Yeah. So during electrolysis, some kind of mass or some mass of that electrolyte may be deposited on the corresponding electrode. And what about that mass? Here the first law deals with that, the relation between that mass and the amount of electricity passed. We all know that if greater amount of electricity passed, then greater will be the reaction, greater will be the deposition, greater will be the mass deposited, right? Yeah. If a huge amount of current is passed, then greater will be the electrolysis process, which means greater will be the deposition of A and B minus. Okay. Ready? And one more thing is that if the deposition is for a solid, then we are if the deposited atom is a solid. For example, if I have Na, okay, Na deposited like this. If I have Na plus and it is deposited as Na solid, right? Yeah. Then if the deposited particle is a solid, then a discharged particle, this is simply said to be discharge of ions from solution to electrode. Ready? If the discharged particle is a solid, then it is said to be deposition. What? Deposition. Similarly, if the discharged particle, let me discharge the Cl minus, chloride ion to chlorine gas. through oxidation. And if the discharged particle is a gas, then ions are discharged on that electrode. Okay, and the liberation which is used for your gas or discharging of gas, and deposition which is used for the discharging of solid. Ready? Fine. So your Faraday's first law that deals with the mass of substance discharged, and amount of electricity passed. Amount of electricity passed and mass of substance discharged. We all know that if greater amount of electricity passed, greater will be the mass deposited, right? Which means it is directly proportional. Amount of electricity directly proportional to mass of substance discharged. Okay, the Faraday's first law is that mass of substance discharged. Discharged means deposited or liberated, and the terms may used for the proper criteria. Okay, so mass of substance deposited or discharged, or mass of deposited or liberated, or simply mass of substance discharged. Let me define the mass using the simple W. Is directly proportional to amount of electricity passed. Amount of electricity passed through electrolyte. Okay. Amount of electricity means it is a charge in Coulomb. What it is? Charge in Coulomb. Okay, which means I ampere current that passed for t second. That is said to be amount of electricity. And that is the Faraday's first law. So the mathematical expression is, so it is okay. If greater amount of electricity is passed, greater will be the discharge. So greater will be the deposition or liberation. Fine. So simple law. So W that is proportional to Q in a mathematical sense, or your W is equal to ZQ. W is equal to ZQ, where Z is known as electrochemical equivalence. What it is? Electrochemical equivalence. So Z is said to be electrochemical equivalence. Fine. What about the expression for Z? Yeah, Z is equal to W by Q. Okay, we can write it as all we know that charge is equal to product of current into time. So Z is equal to, Q equal to ZIT. Q equal to ZIT. Okay, so the expression for Z will be Z is equal to W by Q, or Z is equal to W by IT. So what about the unit of your Z? It is gram per coulomb, or gram coulomb inverse, or gram ampere inverse second inverse, right? Yeah. So you don't expect that the question may ask like this if you are given with the value of Z, I, T, and you're asked to find the W. The question may not ask like that. Okay, question is asked from this concept in relation with the equivalent concept. Equivalent concept. Ready? So question may ask using the Faraday's first law, which is in relation with the equivalent concept. Okay, so let me define how that equivalent concept is connected with the Faraday's first law. Okay, so that is, let me define that. So you're okay with the Faraday's first law? Fine. Let me erase the figure of electrolytic cell. Now we are in the expression for the Faraday's first law, right? W equal to ZQ, and we know that is EQ. Is that something like that? Okay. The main important point, the very important point is that of 1 mole electron. What is the value of charge of 1 mole electron? The charge will be 1 mole electron means we know that the charge of 1 electron is 1 into 1.6 into 10 raised to minus 19. And if it is 1 mole means 6 into 6.022 into 10 to the power 23, right? Yeah. So if we pass a current of 1 mole electron, that means what is that magnitude? That is 1.6 into 10 raised to minus 19 into 6.022 into 10 raised to 23. And it is clear that, or the value will be 96500 coulomb. 96500 coulomb. It is actually 96487 coulomb and is approximately taken as 96500 coulomb. So let me define an important point. That point is that if you passed an amount of electricity of charge electricity of 1 mole electron, then what is that charge in coulomb? The charge in coulomb is the charge of 1 electron, that is 1.6 into 10 raised to minus 19 into, if it is 1 mole means we know all that, into Avogadro number, and the value in coulomb will be 96500 coulomb. And this is simply defined as 1 farad. 1 farad. If you passed a 1 farad current, that is a simple sense. If you passed 1 farad current, which means 96500 coulomb current, then equivalent mass of substance deposited. Equivalent mass of substance deposited. Then equivalent mass of substance deposited. Are you okay with that? Are you okay with that? So simply equivalent mass of substance deposited means 1 equivalence deposited. Equivalent mass deposited means 1 equivalence deposited. Okay, fine. So simply 1 farad equal to 1 equivalent mass. 1 equivalent mass, which means 1 equivalence. So 1 farad means for any electrolyte, it is 1 equivalence. It is the amount which is equal to, if you passed 1 farad current, then that electrolyte will liberate or deposit its equivalent mass, which means it's 1 equivalence. That is a main important point. If you passed 1 farad, then you obtain 1 equivalence. If you pass 2 farad, then you obtain 2 equivalence. If you pass 10 farad, then you obtain 10 equivalence. Generally, if n farad passed, what happens? N equivalence deposited. Is it okay? Yeah. If n farad passed, then what do you obtain? You obtain n equivalence. Okay. This is one of the important point, and let me define one more point. For a reaction, let A is an cation. A is a cation. Ax plus is the charge. A is a species, and X plus electron is dropped from that. Okay, and we all know that if it gain X electron, then it become or it discharged as A0, right? Yeah. Then it discharged as A0. Then for this reaction, this is okay for you? X plus is a species, and if it gain X electron, if A3 plus, then for 0, how much electron it should gain? 3 electron. Like if it is X plus, for 0, then it should gain, in order to have 0 charge, it should gain X electron, right? So then if you passed X farad, if you passed 1 farad, then what happens? Equivalence, 1 equivalence of A deposited, fine. But the main point, this is already defined, but I preferred you to study this point. What? If X farad passed, not 1 farad, X farad. X farad means the farad current which is corresponds to the electron involved. Farad current which corresponds to the electron involved. That is X farad here. So if x farad passed, then 1 mole substance deposited. 1 mole, no need of 1 equivalence deposited, here 1 mole deposited. Is it okay for you? For example, I have Al3 plus, and we know that Al3 plus become, or Al3 plus discharged as Al. For that, it should absorb what? 3 electrons. Then if 1 farad passed, equivalence means equivalent mass deposited, or equivalence deposited means 27 by 3. You know how to find the equivalent mass. Molar mass divided by n factor. We already discussed it in your redox reaction, some basic concept. So 1 farad passed, equivalent mass deposited. Equivalent mass deposited means 27 divided by 3, 9 gram deposited. Or if 3 farad passed, 1 farad passed, equivalence deposited. Equivalence deposited means equivalent mass deposited. 1 equivalence means 1 equivalent mass. Equivalent deposited means equivalent mass deposited. 1 mole deposited means molar mass of that substance deposited. Molar mass deposited, not that point. 1 equivalence, which will be numerically equal to equivalent mass of that substance, and 1 mole, which will be numerically equal to molar mass of that substance. So 3 farad, 1 mole deposited. 1 mole deposited means molar mass deposited, and the molar mass of aluminum is 27. So this is a main point. Similarly, if you have an anion, let I have an anion. So By minus is anion, and we all know that By minus become B0 by the removal of Y electron, right? Yeah. Then what is the electron involved here? I'm sorry. First of all, if 1 farad passed, what happens? Equivalence deposited or equivalent mass deposited. There is no change in it, or no, there is no change in it. This is a universal concept. If 1 farad passed, equivalence deposited or equivalent mass deposited. But for here, what is the number of electron involved? X electron? No. In the previous case, it is okay, X electron. But in this case, it is Y electron. So, if you passed farad corresponds to electron involved. If you passed farad corresponds to electron involved. The farad corresponds to electron involved means you passed Y farad. The electron involved is Y electron. So, you simply pass farad which is corresponds to the electron involved. So, we all know that the electron involved is Y. So, simply we pass Y farad. So, if Y farad is passed, then molar mass deposited or mole deposited. Is it okay? I'll give you one example. Let I have O2 minus, and we all know that O2 minus become half O2 by the liberation of 2 electron. Okay, so 1 farad passed, equivalent mass deposited. Equivalent mass of that oxygen is 16 divided by 2. We all know that equivalent mass is molar mass divided by n factor. N factor for an anion, I think you are familiar with that. It is 2, so 8 gram. Ready? Therefore, simply, what is the electron involved here? Yeah, 2 farad. Sorry, 2 electron. So 2 farad passed, molar mass deposited. Molar mass is 16. Both are same, right? Yeah, 1 farad passed, 27 by 3. 3 farad passed, 27. So you can use any one of this. I'll prefer this. This is a very important point in my view. Okay, because something which is connected with the mole or molar mass will be more easy than with the equivalence or equivalent mass. Okay, so listen here. So this is, let me define the most important point from here. If current of electron involved farad the current of electron involved farad Here is electron inward is X, so X farad. Here the electron inward is Y, so Y farad. Passed. If this much current is passed, how much? Electron involvement times of farad. And how you know the electron involvement? By looking the reaction. Then 1 mole substance deposited or discharged. 1 mole substance discharged means molar mass discharge. This is the most important point in my view. Okay, ready for you? Okay, so let me modify the equation of your Faraday's first law using this one. Connection of this concept, equivalent concept with your Faraday's law. That is, we know that W equal to ZQ or ZIT, right? Fine. And we know one more thing, that if the supplied current is 96500, if the supplied charge is 96500, then the weight deposited will be equivalent mass. So weight deposited will be equivalent mass. That is the idea we just discussed in the previous section. Okay. So simply substitute this idea to here. What? Weight will be E into 96500. So we simply obtain an expression for your Z. That is, Z is equal to, Z of any substance is equal to its equivalent mass divided by 96500. Therefore, what will be the expression ZQ? W equal to, instead of Z, simply write E divided by 96500 into Q, or W is equal to E divided by 96500 into current into time. And this is the most important equation in your Faraday's first law. Okay, ready? Let me introduce some tricks. That is, 1 divided by 96500, you can simply write it as 1.04 into 10 raised to minus 5. 1.04 into 10 raised to minus 5. And 60 into 60 divided by 96500 will be equal to 0.04. 0.04. Actually, it is 0.036. Simply 0.04. Ready? Okay. This will be useful for you. And the 60 into 60, that is, if the time is given in hour, then you should convert it into second. So there will be, for example, 3 hours. Then you supply the time as 3 into 60 into 60. And that 60 into 60 divided by 96500, you can simply write it as 0.04. It will be an advantage for you. Okay. Let me have one question. Find Z of aluminum. Okay. So how we can find the Z value? Equivalent mass divided by 96500. What is the equivalent mass of aluminum? Equivalent mass is equal to molar mass divided by N factor. Molar mass of aluminum 27. N factor is the positive charge. We all know that aluminum can only show Al3+. So the positive charge is 3. So 9 is the equivalent mass. So 9 divided by 96500. So no need of dividing with this one. You simply bring the 96500 to the top. That is 1.04 into 10 to the power minus 5. Mass. So this is a concept of Faraday's law. Ready? Mathematical equation. Ready? So let me do some problems. And I think more and more problems will be there in your discussion paper. Okay. So that's all about the theory. So now you wanna find, or you wanna see some kind of problems. That is, how much mole of electricity required, sorry, how much farad of electricity required for the reduction of mm, 0.1 mole MnO4 minus in acidic medium. So you have to know that the permanganate in acidic medium turns to Mn2 plus. Okay, that is the concept that we already discussed in your redox reaction. So what is the number of electron involved here? We all know that permanganate, the manganese is in plus 7, and now it is in plus 2. So the number of electron gained is 5 electron. So we know the concept. The electron involved is 5. So 5 farad supplied, 1 mole reaction takes place, right? What is the number of electron involved? That much farad supplied, 1 mole change will happen. So 5 farad supplied, then 1 mole MnO4 minus produced. But we want to reduce what? 0.1 mole MnO4 minus. So if you want 0.1 mole MnO4 minus for the reduction, you should divide here with 10. Then only your 1 become 0.1. So if the RHS divided by 10, then your LHS also divided by 10, right? So it is clear that 0.5 farad of current is required for the reduction of 0.1 mole MnO4 minus to, MnO4 minus to Mn2 plus. Okay. So the basic idea is that 5 electron involved, then 5 farad supplied, 1 mole changed. You have to keep that idea. Okay. This is one kind of question. Let me do the next. Listen. If 3 farad current passed through molten NaCl, MgCl2, AlCl3, find the ratio of moles of sodium, magnesium, aluminum depositor. So you want to find the molar ratio when 3 farad current is passed through that typical electrolytes. So we want to find the ratio of sodium, magnesium, aluminum. So we want to simply choose the Na plus from here, Mg2 plus from the second one, Al3 plus from the third one. Okay. So it is clear that how the reduction of Na plus takes place. Na plus 1 electron gives Na. Mg2 plus 2 electron gives Mg. Al3 plus 3 electron gives Al. So what we can write from here? Electron involved is 1 farad. 1. So 1 farad supplied, 1 mole sodium depositor, right? Electron involved times of farad supplied, then 1 mole of substance reacted. Here electron involved is 2. So 2 farad supplied, 1 mole magnesium deposited. Here electron involved is 3. So 3 farad supplied, 1 mole aluminum deposited. Ready? Okay, but what we supplied 3 farad. Therefore, what will be the value for 3 farad? 3 farad, 3 mole sodium. For 2 farad, 1 mole, then 3 farad, 3 by 2 mole magnesium. For 3 farad 1 mole, we are also giving 3 farad, so 1 mole. So the ratio of moles will be in the order 3 is to 3 by 2 is to 1. So if you all multiplied using 2, 6 is to 3 is to 2. Let me show another kind of problem, that is find molecules of hydrogen liberated at cathode and also volume of fluorine liberated at anode when 4 farad current passed through HCl. If 4 farad current is passed through HCl, what happens? Okay, listen here. We know that HCl become H plus plus Cl minus. So these are the ions. What about the reaction? The reaction cathode, that is 2H plus. 2H plus which accept 2 electron forms 1H2. Ready? Is it okay? Like that. What is the reaction in anode? 2Cl minus become a chlorine by dropping 2 electron. So it is clear that the electron involved is 2. So 2 farad supplied, 1 mole hydrogen deposited. Here also 2 farad supplied, 1 mole chlorine liberated. So answer is over. What you are asked to find? What you are asked to find? 4 farad passed. Find the molecules of hydrogen liberated at cathode. If 2 farad, 1 mole means, therefore for 4 farad, 2 mole hydrogen. But you are asked to find the molecules of hydrogen. 2 mole hydrogen means 2 into Avogadro number molecules hydrogen. Okay. Here 2 farad supplied, 1 mole chlorine liberated, but we supplied what? 4 farad. So 4 farad means 2 mole chlorine liberated. If 2 mole chlorine liberated means, what you're asked to find? The volume of chlorine at STP. At STP. So 2 mole chlorine, what is the volume at STP? 2 mole, 2 into 20.4, 44.8 liter chlorine at STP. Okay. So question also asks like this. Ready? Okay. The next question, that is, when molten AlCl3 electrolyzed with a current efficiency of 50%, Okay. Find the farad current required to deposit 90 gram aluminum. It's a good question. So when molten AlCl3 electrolyzed with a current efficiency of 50%. What do you mean by current efficiency? It is the efficiency of that current, which means if you supplied 1 ampere, 1 coulomb, listen here, if you supplied here 1 coulomb, then for 100% efficiency, we obtained here 1 coulomb. The input will be equal to output. I think you are familiar with the efficiency. Efficiency is output by input, right? So, if input by output, we know that efficiency is output by input. If that into 100, if that efficiency is 100, which means 1, ratio is 1, means what is the input, that much output we obtain. What about the efficiency 50% into 100, which means output by input is 1 by 2. Which means if input is 2, output is 1. That is the concept. If we supplied 2 amps current here, we obtain the output as 1 ampere. That is the meaning of 50% current efficiency. What we supplied, its half will be used, or half will be availed, or half we obtained. Okay, fine. So we electrolyzed what? Molten AlCl3. Molten AlCl3, we know that for the electrolysis of in the electrolysis of molten AlCl3 to aluminum, the reacted species is Al3 plus, no doubt. In the previous question, both are reacted, right? Or both are mentioned. Find the molecules of hydrogen and find the molecular volume of chlorine, means we have to consider the cation and anion in that particular HCl electrolyte. But here we are given with the LCl3 electrolyte and we are asked to find the questions of or the data of your aluminum. So we simply choose the Al3 plus from that. Okay, yeah. So Al3 plus 3 electron gives what? Al. So what you are asked to find? We want to deposit 90 gram. Then how much farad is required? Okay, if 100% efficiency, 100% current efficiency, what is the logic? We know that 3 farad, electronic load is 3 farad supplied, 27 gram aluminum deposited. Ready? Then to get 90 gram aluminum, how much farad supplied? Let it be X, right? We need 90 gram, how much farad? Simply cross multiply. You know that concept. Cross multiply. 3 into 90 equal to X into 27. So this is 9. So X is equal to 10. So it is clear that 10 farad required for 90 gram deposition. 90 gram deposition required 10 farad. Okay. If it is an ideal case, if the current efficiency is 100%, but our current efficiency is 50%. So to obtain 10 farad output, we have to supply 20 farad. Actually 90 gram required 10 farad. No compromise in it. 10 farad output can provide 90 gram deposition. But here the current efficiency is only 50%. So you should supply 20 farad here. Ready? So supply 20 farad. Is it okay for you? Okay. So this is one model of question in your electrolysis. What about the next model? Let me show one more kind of model. Listen here. $45 aluminum deposited equal to -gram copper deposit. It's a good question. The question is that if a cell were 45-gram aluminum deposited, then if you remove that cell and we supply the same kind of current, how much copper deposited? Fine. So let me find how much farad is required for aluminum. We know that 1 farad supplied the 9-gram equivalence of aluminum deposited. So to get 45-gram aluminum, we must supply 5 farad. Okay. So using 5 farad current, how much copper deposited? We know that for 1 farad current, copper will deposit its equivalent mass. What is the mass of copper? 63.5 divided by 2 is, I think that is 37.5 gram, right? Yeah. 1.75, yeah. So 1 farad may supply 31.5, but we actually deposited here 5, or we actually supplied 5 farad. So 5 into 31.75. Okay, multiply a number with 5. What is the case? You simply take its half. What is half of 31.75? Half of 50 is 15 plus half of 1.75. 1.75, the half is 1.75, the half is 175, the half is 170, the half is 85, 82.5. So it will be 15.825, right? I think. Is it correct? 15.825 is the answer. Find the half and multiply 10 using that. Then you obtain the answer. Let me check whether it is correct or not. Have a doubt. 5, 2, 35, 37, 3, 5, 8, 15. 15.75. How become 75? How become 75? Leave it. Okay. So one more topic is here in your Faraday's law. That is Faraday's second law. It's very easy. Faraday's second law. That is, if you have an electrolyte, E1, another electrolyte, electrolyte 1, electrolyte 2, and 2 electrodes are dipped in it. They are connected by a battery, positive, negative, and in order to complete the circuit, an arrangement like this, negative, positive. So this is a series connection of two electrodes. Series connection of two electrodes. Ready? There are two different electrolytes. Electrolyte number 1, electrolyte number 2. But they are connected in series. Different electrolyte connected in series. If two different electrolyte is connected in series, then what is the mass deposited? That will be proportional to their own equivalent mass. So if any kind of current is passed here, for example, 1 farad current is passed, then the equivalent mass of this substance deposited here. Because series connection means current will be same. If 1 farad supplied here, we obtain 1 farad here, 1 farad also here. So 1 farad supplied means we know that equivalent mass deposited. So 1 farad supplied means here the equivalent mass deposited. Here also equivalent mass deposited. But equivalent mass of electrolyte number 1 will be entirely different from the equivalent mass of electrolyte number 2, right? Yeah. So how much current is passed, then the deposition will be proportional to their equivalent mass. For example, 10 farad current is passed, then 10 into equivalent mass of electrolyte 1 will be deposited here, and 10 into equivalent mass of electrolyte 2 will be deposited here. So whatever be the current passed, if they are in a series connection, two different electrolytes are in a series connection, then whatever be the current passed, then the deposition will be proportional to their own equivalent mass. So different electrolyte connected in series, then mass discharged, then the discharged amount will be proportional to whatever the current supplied, the discharged amount will be supplied proportional to their own equivalent mass, which means here the discharged amount proportional to equivalent mass of the electrolyte number 1, and here the equivalent mass discharged amount proportional to equivalent mass of electrolyte number 2. That is the concept, okay? Condition is applied, there are two different electrolytes and they should be connected in series, which means the same amount of current is passed in the very same time for the two electrolyte, okay? So the different electrolyte connected in series, then the mass discharged will be proportional to their own equivalent mass. Their own equivalent mass. For example, here the mass deposited proportional to equivalent mass of that substance. Mass deposited is in your electrolyte number 1, that is W1, and it is proportional to equivalent mass of that electrolyte, that is W1, E1. And here the mass deposited is proportional to, let it be W2, proportional to E2. Then if you have the ratio W1 by W2, then since it is proportional to E, it will be E1 by E2. Since we know that Z equal to E divided by 96500, right? So we know already that Z proportional to E or E proportional to Z, then this ratio will be equal to Z1 by Z2. So this is a numerical relation which is used in your Faraday's second law. Okay, so Faraday's second law is very simple. That is, if we have more than one electrolyte, no need of two. If you have more than one electrolyte, but they should be in a series connection, okay? Then, what are the currents applied? Their deposition or mass deposited. We know that by passing the current, the current will be equally transmitted to the all electrolyte. Whatever be the magnitude of current, that doesn't matter. The deposition in each container in accordance with their own equivalent mass. The deposition of first container in accordance with the equivalent mass of first one, second one, third one, like that. Okay. So mass deposited proportional to their own equivalent mass. That is the concept. Okay. Fine. So that's all about the quantitative aspect of electrolysis in my view. We can discuss the qualitative aspect and moreover the questions from your material.